Hello everyone. Today let us start magnetism. So the magnetism it developed from the word magnesia. Okay, the magnet it attract the magnetic material. You have a you know you can see here, this is the magnet. The magnet has a north pole, the red, this is the north pole and this is the south pole. And let us suppose you have a wire, this is the wire, and this is your switch, and here you can write here you can connect the source, current source, and right here this is compass needle. Look at this, the circuit is right now open circuit, and simply the compass needle points north and south. Compass needle always points north and south. That is due to the earth magnetic field. We'll talk about that. Okay, so here the needle points north and south, and there is no current in the circuit. Now if you turn on the circuit is now closed circuit. So if you turn on, then you will see the deflection here in the compass needle. Compass needle deflect in that case. That means when the current is flowing through the circuit, the compass needle deflect. What does that mean? That means the magnetic field develop here, there. That is why this compass needle deflect. That means current produce the magnet. Okay, so the current produces the magnet. Current produce the magnet. Is reverse true? Magnet can produce the current, then we'll talk about that. Okay, so this is the current produce the magnet. This is Oersted discovery. Okay, Oersted discovery. So the current produce the magnet. Okay, now the magnet has a north pole and south pole. So if you draw the magnet has a north pole and south pole. Okay, so north pole and south pole. If you cut the magnet, if you break it into two parts like this, what happened? Here you have a north pole, this is your south pole. Then what happened is south pole develop here and north pole develop here. So if you break the like this is your magnet, then if you break it, then it results two magnet. Okay, so even if you further break it like this, if you make two more like this, in this case also, look, another two magnets. So no matter how many times you break, how small piece you make, there is a north pole and there is a south pole, because magnetic monopole never exists. Okay, magnetic monopole never exists. But we talk about the electric monopole. Electric monopole means like if you have a positive charge, or you can have a negative charge, you can have a single positive charge, you can have a single negative charge. That is an electric monopole. That is possible. But the magnetic monopole never exists. You cannot single out the north pole, you cannot single out the south pole. If there is a north pole, there must be the south pole. That is why we said magnetic monopole never exists. Okay. Okay, let us draw again. This is your magnet, north pole here, south pole there, and you know, if you have proton and electron at a certain distance, equal and opposite charge at a certain distance, we call as the electric dipole. This is the electric dipole. Then you can draw the electric lines of force. Electric lines of force start from positive charge and terminate at the right here. So negative charge. Start from here and terminate there. This is the electric lines of force. Okay, electric lines of force. We talk about this already. Electric lines of force. Similar to the electric lines of force, we can draw the magnetic lines of force. Magnetic lines of force start from the north pole. Magnetic lines of force start from the north pole, but don't say terminate at the south pole. Magnetic lines of force start from the north pole and move toward the south like this. It is a closed loop. If you want, you can draw here also, inside the magnet. Magnetic lines of force is the closed loop. Magnetic lines of force is a closed loop. Magnetic lines of force are the closed loop. But of course, the magnetic lines of force, they start from the north pole. Okay, so if you want, you can draw as many as you want, like this. Oh, this is wrong. You have to start from north to south. So if you want, you can draw another one this way. Here also you can draw this way, or if you want, you can draw this, you can draw this, and here you can draw this way. So this is the magnetic lines of force. And the magnetic lines of force, look, they are crowded near the pole here and there. If the magnetic lines of force, if they are crowded, more lines there, at that point the magnetic field strength is maximum. Strong magnetic field right here and right there, because the magnetic lines of force, they are crowded there. Similar to here, the electric field, they are the electric lines of force, they are crowded here, so the electric field is maximum right there. If you are close to the charge, electric field is more. If you are away from the charge, electric field is less. Same thing here, the magnetic field is more near the pole, and if you move away from the pole, the magnetic field is less, is small. Okay, that's one point. The first point, magnetic lines of force, they are closed loop. Start from the north pole, but they form a closed loop. Second point, magnetic lines of force start from north pole. Okay, and you know, the magnetic field strength is more near the pole, because the magnetic lines of force, they are crowded near the pole. They are concentrated near the pole. And another point, the magnetic lines of force, they never intersect to each other. The magnetic lines of force, they never intersect to each other. Why? Again, look at this. This is north pole, this is south pole, and if you draw one magnetic lines of force like this is your magnetic lines of force. If you draw another ones like this, look, they intersect right here. This is not correct. You cannot do this. The magnetic, two or more than two magnetic lines of force, they never intersect to each other. Why? Because this is not correct. Okay, you cannot do this. Why? Because if you draw the magnetic lines of force like this, let us suppose this is your one magnetic lines of force, and right here, for example, right at this point right here, if you draw the tangent line, this is the tangent line. If you draw the tangent at this point, this tangent line gives you the magnetic field at that point right here. This tangent line, this is the tangent line. Okay, this is the tangent line. This tangent line gives you the magnetic field at this point. Okay, if you draw the tangent at any point on the magnetic lines of force, that tangent line gives you the magnetic field at that point. Okay, so the tangent drawn at any point on the magnetic lines of force gives magnetic field. Simply magnetic field is denoted by uppercase B and it is measured in Tesla. The unit of magnetic field is Tesla. Gives the magnetic field at that point. So if you draw the tangent at any point on the magnetic line, suppose that tangent line gives you the magnetic field at that point. Magnetic field, it is denoted by B, uppercase B, and the unit, SI unit is Tesla. Okay, or if you want to use the smaller unit, the smaller unit is Gauss. Gauss is the smaller unit of the magnetic field. Okay, so now you know this. If you draw the tangent here, that gives you the magnetic field. If you draw the tangent right there, for example, at this point, if you draw the tangent like this is also the magnetic field. Because I mentioned that the tangent line gives you the magnetic field. Okay, now I said two or more than two magnetic lines of force, they never intersect. What happens if they intersect like this? If they intersect something like this, like look, this is the point of intersection. So right here you have a two curve. One is if you draw the tangent this direction here, and if you draw the tangent on the second line, this is the another tangent line. So you have a two magnetic field there then. That is not possible. That is not possible. That is why two or more than two magnetic lines of force, they never intersect to each other. Two or more than two magnetic lines of force, they never intersect to each other. Okay. So the magnetic lines of force, the strength of magnetic field, that depends on the magnetic lines of force. If you have a more magnetic lines of force, we also call that magnetic flux. The magnetic flux is how many like this. If you have the certain surface area here, how many magnetic lines of force passing perpendicularly through this surface area, that is called as the magnetic flux. So simply the magnetic flux is magnetic lines of force passing per unit area, and the magnetic lines of force that must be perpendicular to the surface. That is called as the magnetic flux. So simply the magnetic flux is the magnetic lines of force. And the magnetic flux determines the magnetic field. So if you have more magnetic lines of force, magnetic field is big there. If you have a less number of magnetic lines of force, the magnetic field is small. And again, the unit of magnetic field is Tesla, SI unit. The smaller unit is Gauss. Okay. And I also mentioned that the Oersted discovery, the current produced the magnet. So if current produced the magnet, then you need to know the direction of magnetic field and direction of current. Okay. For example, let us suppose this is the wire. This is the wire and current is in this direction. So this current produced the magnetic field here. So how do you figure out the direction of magnetic field? Let us let me find something else. Okay, so I don't have anything. So let us suppose this is a conductor. Consider, okay, this is a conductor and current is upward direction. Current is upward direction. So what is the direction of magnetic field then? How do you draw the magnetic lines of forces? You have to use the right hand rule. Right hand rule. What is right hand rule is, use your right hand. This is a conductor like a wire, okay, and grab the conductor using your right hand like this. Now look at this. I grab this conductor and the current is up. Look, my thumb. The thumb is in the direction of current. Okay, thumb is in the direction of current. And the curl finger, these four fingers, they curl like this. This gives you the direction of magnetic field. So again, look here, you grab something like this here. The conductor, the blue marker, that is I consider conductor. Thumb pointed at this. This is the direction of current, up. and the magnetic field is this way, right hand rule. Don't use your left hand rule. So if the current is up, magnetic field is this way. Now if the current is down, how do you figure out the magnetic field then? You use the left hand? No, don't use your left hand. You have to use again right hand, but do this way. So look, thumb point downward this way, okay? Thumb point downward, this is the direction of current, and this is your magnetic field, this curl finger. This is how you have to figure out the direction of magnetic field. This is a right hand rule. So what happened here is, if the this conductor, the current is up, so this way, up, and look, up, this way, okay? So your magnetic field is, you have to draw the, like a circle, closed loop. This gives you the magnetic field, this, so the magnetic field encircle the wire, conductor. So if you have a, if this is a conductor, current is up, and your magnetic field is closed loop like this. The magnetic field, the magnetic lines of force, you have a closed loop. This closed loop encircle the conductor. That means, look at this. So this is how you draw. But for example, if you want to get the magnetic field there, so what is the direction of magnetic field then? How do you figure out? I said this gives you the magnetic field. But of course the magnetic field is not like a circular. The magnetic field, it is a vector quantity. It has a magnitude and direction both. So how do you get the direction right here then? Look, first look at this arrow. This arrow, it is this way, okay? So if you want to get the magnetic field right here, draw the tangent then. So this is the magnetic field at this point, let me call V1. Or if you want to find out the magnetic field here, so what is the direction of magnetic field? Here the direction of magnetic field is up. What about there? It is down there. And if you want to find out the magnetic field here, draw the tangent. This is V3. So this helps you to draw the magnetic lines of force. Like the right hand rule help you to draw the magnetic lines of force. The magnetic lines of force, it is a closed loop, and simply if you have a conductor, a straight wire, in this case the magnetic lines of force encircle this conductor. Then if you have a closed loop, you can draw the tangent at any point where you want to find out the magnetic field. Okay, so at any point you can easily figure out the direction of magnetic field. Okay, so this is your right hand rule. This is your right hand rule. So you use the your right hand rule. Please don't use the left hand rule. So this is what you need to know. This is your current. So the curl finger gives you the magnetic field. Okay, so it is something like this. This is your, if you draw this way, something like this. Okay, here this is your current, this is your magnetic field. This one, you need to know this. Okay, so this is the curl finger, that gives you the magnetic field. Thumb is in the direction of current. Okay, so this is about the right hand rule. And if you have, let's say, wire, this is the wire, this wire carries the current I, and I want to calculate the magnetic field right here at this point, and this point is at a distance, let us suppose R from the conductor. So how do you get the magnetic field here? So you use the right hand rule, then draw the one circle like this way. Like this. Okay, so magnetic field is, using the right hand rule, it is this way. Now I want to calculate the magnetic field at this point P, let me call point P, which is at a distance R from here. This is perpendicular distance, and right here, of course, using the right hand rule, this is the direction of magnetic field B. This gives you the tangent line, that gives you the magnetic field. Of course, you can get the direction there. But what is the magnitude of this magnetic field B? It depends on the magnetic field at this point. This point is at a distance R from the conductor. It is, the magnetic field B is directly proportional to the current, and inversely proportional to the distance, this R. Okay, and this is proportionality sign, so you can write down B, magnetic field B, this is equal to mu naught divided by 2 pi I divided by R. So it is the formula mu naught I divided by 2 pi R. You can use this formula to calculate the magnetic field due to the current carrying conductor. Okay, so here the mu naught, this is a constant, and this is equal to 4 pi times 10 to the power negative 7. This is the magnitude. Mu 0 is 4 pi times 10 to the power negative 7 Tesla. This is Tesla meter divided by ampere. This is the unit. So mu 0, 4 pi times 10 to the power negative 7 Tesla meter per ampere, and this is called as the permeability. Okay, so this is the permeability of free space or simply air also. Permeability of free space or air. So this is the formula B equal to mu naught I divided by 2 pi R. Okay, if you are interested. Okay, so the magnet, I told you that if you bring the compass needle and if you keep the compass needle here, compass needle points north and south, or if you suspend this magnet using some kind of thread rope, this bar we call the bar magnet. The bar magnet also always points north and south. If you suspend this using use a thread string and suspend this, the bar magnet also points north and south. You know that the magnet, what happen is, if you have a two magnet, the blue is south and red is north, and in electricity chapter you learn that like charge repel, unlike charge attract. Proton and proton repel, electron and electron repel, but electron and proton attract. Similar to that, if you have a like pole, look, this is the north pole, red one, south pole, red one is the north pole, and another red one, this is also north pole. I have a two bar magnet, red is the south. Now if I bring the south pole together, look, I try to bring them in contact. I am not applying a huge force because the magnet is not very strong. Look, they repel. I try to bring them in contact. No, they repel. Like pole repel. But now look at this. South pole also, they are like pole. Look, they repel. I cannot bring them in contact. It is really difficult because there is a repulsive force. But now south pole and north pole, unlike pole, what happened? Look, they attract. Look, unlike pole, north pole and south pole, they attract. But south pole and south pole, look, south pole and south pole, they repel. North pole and north pole, they repel. So you need to know that north pole and south pole, they are unlike pole, they attract. South pole and south pole, or north pole and north pole, they repel. Like pole repel. Okay. And what happened in case of compass needle then? Compass needle point north and south, because if you draw the arc, you have to draw kind of sphere. It is not, earth is not perfect sphere, but still you have to draw. Consider, okay, this is earth, and if you draw the axis, this right here, this is your geographical north pole, and right here you have geographical south pole, and there is a earth magnetic field. You know, if you go inside the earth, there is a semi-liquid. Due to that motion, there is a magnetic field created there. Don't think there is a big physical magnet sitting there. No, that is not the case. But due to the motion there is a semi-liquid, there is a the magnetic field, and the magnet we call the earth magnet. If I draw something like this is the axis of the earth magnet. If I draw, this is my magnet, okay, this is my magnet. Right there you have S, south pole of the magnet, and right here you have N, north pole of the magnet. So near the geographical south pole of the north pole of the earth, near the geographical north pole, the magnet has this is magnetic south pole, magnetic south pole. Near the geographical north pole there is a magnetic south pole, and here near the geographical south pole you have a magnetic north pole, magnetic north pole. And you can see that geographical north pole and magnetic south pole, they do not coincide. There is an angle. Look, this axis, if you see, this is the magnetic axis, okay, and this is the earth axis, this is the earth axis. So they have not coincide. So if you draw different color, this is a magnetic axis, and there is an angle, there is an angle. They do not coincide, they do not coincide. There is a, you see, there is an angular difference here. They do not coincide. But what you need to know is near the geographical north there is a magnetic south pole. Now what happened is, if I suspend this bar magnet, the compass needle is tiny bar magnet, you can think that way. If I suspend this bar magnet using the thread rope, what happens is the north pole of this bar magnet is attracted by this south pole. The north pole of this bar magnet is attracted by the magnetic south pole of the earth magnetic field. So this north pole is attracted by the south pole. That is why this north pole is always pointing north, or the compass needle, one pole of the compass needle points north, and this south pole is attracted by the magnetic north pole of the earth magnet. That is why if you suspend the bar magnet, it always points north and south. Compass needle is also the tiny bar magnet. That is why due to the earth magnetic field, the compass needle always points north and south. Okay. So that's the one thing I'd like to tell you. Then next is if you have a magnetic field, let us suppose this is the region where you have a magnetic field, uniform magnetic field. Magnetic field you can draw like this. If you draw like this, we say the magnetic field is, in this case I am drawing on the board, so you can say into the board. If you draw the cross mark, if you draw on your paper, if you draw that cross mark, then in that case you have to say the magnetic field is into the page, into the page. Okay. If you draw a different way like this, like a dot mark like this, this is magnetic field out of the page, out of the page, out of the page. B, magnetic field B, magnetic field B out of the page, and this is magnetic field B into the page, into the page. And this is how you draw, okay? Magnetic field into the page, out of the page. This is how you represent, you draw, okay? Now let us do one little bit interesting thing. Okay, force experienced by moving charged particle in the magnetic field. in magnetic field. So the force experienced by the moving charged particle inside the magnetic field. Let us suppose you have a charged particle. This is your charged particle. Charged particle. And this charged particle is moving with a velocity speed v. It is experimentally established that if the moving charged particle enter into the magnetic field, then that charged particle experiences the force, and that force, due to that force, the charged particle moves in a circular path like this. Moves in a circular path like this. So the object, the charged particle, moves in a circular path. Okay, moves in a circular path. So the magnetic force makes the charged particle moving in a circular path. And if the particle is moving in a circular path, there must be the centripetal force. So here what happens is the magnetic force acts as a centripetal force. And the magnetic force experienced by the charged particle, let us suppose Q be the charge. Q, this is charge, okay, this is charge. What is V? This is the speed of the charged particle, speed of a charged particle. Okay, and let us suppose B. What is B? Let us suppose B is here, magnetic field, uniform magnetic field. B is the magnetic field. Magnetic field. And I told you that it is experimentally established that the moving charged particle inside the magnetic field experiences the force. And that force is, we simply represent by F of B. This is equal to B magnetic field, Q charge, V speed sine theta. This is the formula to calculate the magnetic force. This is the force experienced by this charged particle. In this case it is proton. Proton in this case, but you can do the electron also. So this is the formula. What is theta then? Theta is the angle between V speed and the magnetic field. But if theta is 90 degree, what happens then? If theta equal to 90 degree, you know sine 90 degree is equal to 1. Sine 90 degree is 1. Then what happens? This formula becomes F equal to BQV. This is the magnetic force, BQV. So what does this mean? This means if the charged particle is moving perpendicularly to the magnetic field and the speed, velocity, they are perpendicular to each other. Both are vector quantity, velocity, magnetic field. If the charged particle is moving perpendicular to the magnetic field, in that case, the charged particle experiences the maximum force. If the charged particle moving perpendicular to the magnetic field, then in that case, the charged particle experiences the maximum force. Now what happens if the charged particle is moving parallel to the magnetic field then? If the magnetic field and the velocity speed, they are parallel. That means parallel means if theta equal to 0 then, if theta equal to 0, angle between the V and B, if that is 0, if theta equal to 0, what is sine 0? You can use your calculator. Sine 0 degree is equal to 0 then. Then what happens? Your magnetic force, this is BQV sine 0. But sine 0 is sine 0 degree, sine 0 degree is 0. So everything is 0. No magnetic force then. So if the charged particle is moving parallel to the magnetic field, no force there, no magnetic force. I asked these questions in the exam. Okay, suppose the charged particle is inside the magnetic field, but it does not experience any force. What happened there? Charged particle is inside the magnetic field, but no force on it. Why? Either the charged particle is at rest, if it is at rest, V equal to 0, then force is equal to 0. Either charged particle is at rest or the charged particle is moving parallel to the magnetic field. If the charged particle is moving parallel to the magnetic field, theta equal to 0 and sine 0 is, theta equal to 0 and sine 0 is 0. Then if you plug in this equation, you get the force is equal to 0. So here you have three things. You have a force, you have a velocity, speed, and you have a magnetic field. You have a magnetic force, you have a V, and you have a B. All are the vector quantity. Velocity is a vector quantity, magnetic force is a vector quantity, magnetic field is a vector quantity. We have to give the direction then. So how do you figure out the direction then? Again, use your right hand. Again, use your right hand. Okay, use your right hand now. You can do it. This is, let us suppose, this finger is straight finger, this. This gives you the direction of the V, velocity, this. And do this. This gives you the direction of the magnetic field, this. Direction of the magnetic field. And this is your force. Thumb gives you the force. Look here, the straight finger, this is the V, velocity. The curved finger, this is your magnetic field, and thumb gives you the force. Or you can do this way also, like if you want to use three fingers, they are mutually perpendicular. Thumb, this is the force, this is the velocity, and this is the magnetic field. You can use this. If you have to figure out the direction, sometimes it is confusing, okay? So this is the force, this is the V, velocity, and this is the magnetic field. This is also the right hand rule, okay? So if the charged particle moving in the magnetic field and the charged particle experience the force, and the charged particle experience the maximum force if it is perpendicular to the magnetic field, and charged particle, it does not experience any force if it is parallel to the magnetic field. And of course, if the charged particle is at rest, in that case the V is equal to 0, velocity is 0. If velocity is 0, then no force there. Okay, so this is about the moving charged particle inside the magnetic field. And we have another topic. Another topic is current carrying conductor inside the magnetic field. Inside the magnetic field. Current carrying conductor inside the magnetic field. Okay, let me draw the magnetic field like this. This is my magnetic field. I can draw this way also, in this direction. This is the magnetic field. The magnetic field is B. Okay, and I have, this is the conductor, the L1. This is a conductor, and this conductor is inside the magnetic field, and conductor has a length L. L is the length of the conductor, and this conductor carries the current. Current is I. I is the current, and angle between the current I and the magnetic field is theta. L. What is L? Length of conductor inside the magnetic field. Inside the magnetic field. Inside the magnetic field. I, what is I? Current passing through the conductor. Current through conductor. Of course, B, it is magnetic field. Magnetic field. Theta, angle between current I and magnetic field B. Okay, so what happened is, of course, you have to make a closed loop. Okay, I just draw the portion of the conductor only. So you have to connect to the like a source somewhere there, somewhere you have to connect to the source. That is not necessary here. So you have a current carrying conductor inside the magnetic field. So what is current carrying conductor means? In the conductor the electrons are moving. Electrons are moving, and you know that the electrons are the charged particle. We already talked about the moving charged particle inside the magnetic field. So if the charged particle is moving inside the magnetic field, that charged particle experiences the force. So same thing apply here. You have a conductor, but in the conductor there is an electron and they are moving. So electron experience the force, but electron is in the conductor. That means the conductor experience the force. Okay. So if the current carrying conductor is inside the magnetic field, that current carrying conductor also feels some force, magnetic force, and that force, the force experienced by the current carrying conductor, you can again use F of B. This is equal to B I L sine theta. This is the formula. The force experienced by the current carrying conductor is equal to magnetic field B times the current through the conductor I times length of the conductor. This is the length of the conductor inside the magnetic field, just inside, this length only, inside the magnetic field, times sine theta. Theta is angle between I and B. Now when do you get the maximum force then? When this conductor experience the magnetic force, maximum magnetic force. Let us suppose if the conductor is like this. If the conductor is like this, look, this angle is, current is in this direction. Look, this angle is 90 degree. Angle between B and the current is 90 degree. That means if you write down F of B equal to B I L sine 90 degree. Sine 90 degree is 1. So in this case you get F of B equal to B I L. This is the maximum force experienced by the conductor. So if the conductor is sitting perpendicular to the magnetic field, if the conductor is perpendicular to the magnetic field, in that case the conductor experiences the maximum force. The conductor experiences the maximum force. Now what happens if the conductor is parallel to the magnetic field? If the conductor is parallel to the magnetic field, what happens? That means parallel to the magnetic field, you can draw like this. Conductor is sitting this way, parallel to the magnetic field. So in this case, magnetic force is B I L sine theta, but theta, if it is parallel, theta is equal to 0 degree, and you know that sine 0 degree is 0, so everything is 0 then. So if the current carrying conductor is sitting parallel to the magnetic field, that means theta is equal to 0. In that case, no magnetic force. In that case, no magnetic force. Okay. So please note this. Please note this. You need to know this. You need to know this. So if the current carrying conductor is inside the magnetic field, it experiences the magnetic force, and the magnetic force formula is this. You can expect the problem, conceptual questions from here. Okay, so this is about the magnetism. I am not done yet, but I want to stop this video here, and I will talk about the Faraday's laws of electromagnetic induction in my next lecture, next video. Okay, thank you.